quest for more power. It's been a challenge ever since the internal combustion engine was invented.
Today's Formula One racing engines develop incredible power. They're tuned to the nth degree to produce mind-blowing lap speeds on the circuits of the world. But that's all they're good for. If you tried to drive one up the high street, it would soon splutter to a halt. In the real world of transportation, the car engine has to be much more sophisticated. The owner expects it to be reliable, to be smooth, both at low and high speeds, have the best fuel economy ever, and out-accelerate the competition at the traffic light Grand Prix. But the engine also has to satisfy the authorities by having low noise decibels and a clean exhaust. Exhaust emission regulations continue to become stricter and more widespread worldwide. And in recent years, great steps have been taken in the development of fuel injection and efficient electronic engine management systems to meet the requirements.
Of course, the problem doesn't end here. The demand for power and performance continues, but even stricter emission regulations are progressively being planned to take us into the 21st century. At Rover, we are confident that our engine designers are more than equal to the task, meeting the customer's demands and complying with future legislation.
You'll remember the introduction of the exciting all-new K Series engine conceived in 1984 and successfully introduced in 1989. At that time, some critics suggested that 4 valves per cylinder in a small mass-production engine was over-engineering.
But our far-seeing engineers knew better. They had recognized the need to design an engine which could be developed through the 90s to meet future performance and emissions criteria. And that's exactly why the engine continues, and will continue, to be so successful.
Initially, we had the 1.4 K16 engine with single-point fuel injection for the Rover 200, followed shortly afterwards by 1.1 and 1.4 K8 versions, with carburetors for the Metro in 1990. Recently, we introduced the 1.6 Dampliner K16 engine in the new Rover 400 with multi-point fuel injection, and a 1.8 version is being fitted in the MGF.
A policy at Rover has always been to allow shelf engineering. This means our designers are given the freedom to research and develop worthwhile projects not directly linked to any specific model program. In other words, they are given the time to work on a project without the pressure of new model deadlines. When the project proves to be of potential value, it is then put on the shelf until it can be slotted into the company's development plans. One such shelf-engineered project was Variable Valve Control, or VVC for short. Research on it started in 1989 under the codename Hawk, and the development work looked extremely promising, so much so that the design was patented to ensure it couldn't be stolen. It came off the shelf when the decision was made to produce a high-performance version of the 1.8-litre K Series engine for the MGF. Before we look at the Rover VVC itself, let's first take a few moments to remind ourselves of a few of the principles of the 4-stroke cycle of the internal combustion engine.
On the first downward stroke of the piston, the inlet valve is opened by a lobe on the camshaft to allow air-fuel mixture to be drawn in. The inlet valve closes, and on the upward stroke, the mixture is compressed. Near the top of the stroke, the spark plug ignites the mixture, and the resultant high temperature produces a rise in pressure of the gas which forces the piston down on its power stroke. By the time the piston comes up again, the exhaust valve has opened to allow the now used gas to be forced out, and the cycle starts to repeat itself. Now, as you know, in practice, the procedure is a bit more sophisticated than that. For example, the camshaft is designed to open the inlet valve before the exhaust has closed. In this way, the movement of the departing exhaust gas helps to draw in the fresh mixture and create a bigger charge. The inlet valve then stays open through bottom dead center and only closes on the upward compression stroke of the piston. In this way, the pressure differential created by the descending piston during induction and the speed of the incoming mixture ensure the greatest possible filling of the cylinder. After ignition, the exhaust valve opens before the piston reaches bottom dead center again, remains open throughout the upward exhaust stroke, and closes after TDC. As we said just now, the inlet valve will have already opened just before TDC, ready for the next induction stroke. The period when inlet and exhaust valves are both open together is called the valve overlap period. Now, in conventional engines, the design of cam profile and therefore its valve overlap period is fixed, so its shape to open and close the valve is already a compromise between providing the best possible power, economy, idle quality and exhaust emission. But if it were possible to vary the profile, then the opening and closing period of the valves could be changed to suit driving conditions. For example, to get the smoothest idle with the least emissions, ideally you need a very small overlap. For bottom-end acceleration, early inlet valve closure is ideal. And for high-speed performance, the inlets need to open early and close late to maximize the time available to draw in the mixture.
And that is where Rover's brilliant new VVC design comes in, because it does just that. It allows the inlet valve opening and closing period to be changed automatically to suit the performance required. Let's see how it works.
As you know, the K Series engine design incorporates pairs of inlet and exhaust valves. And the first principle to understand is that on the VVC design, larger or smaller overlap is achieved by speeding up or slowing down the turning speed of each pair of camshaft inlet lobes, even though the crankshaft continues to turn at an even rate. Here you can see the time that the valve is open is constant for a given speed of rotation. If the rotation speed of the lobe is slowed down during the time the valve is open, it will stay open for longer and closed for a shorter period of time. Similarly, if the rotation is slowed down when the valve is closed, it will stay closed for longer. And that is exactly what happens in the Rover VVC engine. The pairs of inlet valve lobes can be speeded up or slowed down even though the drive speed of the timing gear is constant, and thus optimize the engine performance under all conditions. To achieve it, the 4 pairs of inlet valves are each driven independently, the front 2 pairs by the timing belt and the rear 2 pairs by a drive belt from the rear of the exhaust camshaft. As you can see here, the drive to one pair is through the center of the other. The clever bit takes place within this drive ring. Let's see if we can explain what happens using this simple animation. The drive ring has 2 slots in it, and the drive from the timing gear connects to one of the slots in the drive ring through a crank. The drive to the camshaft lobe is from the other slot and also through a crank. The position of the drive ring can be moved up or down relative to the shafts, and the slots allow this to happen without distorting the shafts. With the drive ring in the central position, if the timing gear is turned at a constant speed, the camshaft will also turn at a constant speed. If we now move the drive ring upwards, it will turn eccentrically. The drive from the timing gear continues to turn at a constant speed, but you can see that the speed of the tip of the camshaft lobe now changes as it turns. This is because the camshaft crank has to move up and down its slot during each revolution whenever the drive ring is moved from its central position. The principle may be easier to understand if you consider a weight being swung on the end of a piece of string. The weight will travel at a specific speed for a given length of string. If the string is lengthened but continues to turn at the same rate, the weight will have to go faster to complete a rotation in the same time. If you lengthen and shorten the string during the revolution, the weight will speed up or slow down as the length is changed. The same principle applies to the VVC camshaft. Because the pivotal position of its drive pin moves up and down in the slot as the drive ring turns eccentrically, the speed of the cam will change. In practice, the drive is transmitted via pins, and there are drive blocks which slide up and down the slots in the drive ring when it's turning eccentrically. The cause of the eccentricity is another bit of genius. The drive ring turns within this control sleeve, whose internal bore is machined off-center. We'll add the control sleeve to our illustration. By revolving it one way or the other, the degree of eccentricity through which the rotating drive ring is turning will vary, and the speed of the camshaft will change accordingly. So, for example, the overlap can be varied or the inlet valve close point changed to suit the engine performance requirement. So let's see how the control sleeve is turned. It's done hydraulically via this control shaft, which is in mesh with the teeth on the outer circumference of the sleeve. As you can see here, the control shaft is also meshed with a rack connected to a piston in this hydraulic control unit. The control unit receives oil from the engine's pressurized supply and contains a valve to direct this pressurized oil to one side of the piston or the other. When the piston moves, it will rotate the control shaft, which in its turn will change the position of the control sleeve and alter the rotational speed of the pairs of cam lobes.
This section camshaft carrier helps to see the components we've just been talking about. Here are the two pairs of camshafts we mentioned earlier, each pair with its own drive ring and sleeve, but linked by this control shaft. Here is the hydraulic control unit, and you can see its piston and rack in mesh with the control shaft. Movement of the piston is controlled by this valve, which directs oil to one side of the piston or the other.
The position of the valve is dictated electronically by the engine MEMS unit. The MEMS receive signals from the usual sources, crankshaft speed, throttle position and so on. But in addition, on the VVC installation, it needs two more inputs. One is an inlet cam period signal, which it reads from a reluctor ring on the number 4 cylinder camshaft, and the other is an oil temperature signal, so it can allow for variations in oil viscosity as it warms up. The result of the VVC design is that the inlet cam period can be varied by up to 70 degrees, which allows the inlet and exhaust valve overlap to be changed between 21 and 58 degrees. The benefit of all this is a dramatic increase in engine performance over the non-VVC 1800 K Series, 145 PS of power instead of 120, and 174 Newton-meters of torque instead of 166. The engine will rev happily to over 7,000 RPM, and the wide torque band ensures that it will pull strongly even in top gear.
And it's encouraging to know too that for all its power, the engine gives an excellent fuel economy and is already complying with 1997 standards of exhaust emission. So much for the working principles of the VVC design. Before we finish, let's look at servicing aspects. Initially at least, you won't have to worry about overhaul of this very special valve gear. If you get any problems, you should go through the normal prior consultation channels to establish what you should do.
If you are asked to change the head, it's done just like a regular K16, but don't forget this is a damp liner engine and you will need special tool 18G 1736 to hold the liners down whenever the head is removed. The all-important cylinder head tightening procedure is the same as before, and you fit the timing belt in the same way too. The replacement head will be supplied with a rear drive belt fitted, so the two camshafts are already timed to one another, and all you have to worry about is timing them correctly to the crankshaft. Check that the camshaft timing marks are in alignment, and if not, use tool 18G 1521 to turn the gears until they are. Then fit the locking tool 18G1570. Check that the crankshaft marks remain in the safe position. Then fit and tension the belt in the normal way.
Finally, a word about fault diagnosis. In case problems arise, you will be able to use the diagnostic skills of Testbook to help you. As we said earlier, the position of the VVC hydraulic control unit is decided by the engine's MEMS unit, and Testbook is programmed to analyze the whole VVC electronic control system. That completes this introductory training program on our latest exciting new technological development, the K Series engine with variable valve control, another groundbreaking design from Rover Cars, which introduces a new generation of the K Series. The motoring media have been most impressed. We're sure you will be too.